Last time we talked about the continued fraction representation of the square root of 2. This time we're going to continue the series on continued fractions, but we're going to look at a different number. We're going to look at the golden ratio, which is called by some people the most beautiful number in the world. Admittedly, a lot of those people are Robert Langdon in Dan Brown's novel The Da Vinci Code. Continues. As Langdon loaded his slide projector, he explained that the number 5 was derived from the Fibonacci sequence, a progression famous not only because the sum of adjacent terms equal to next term, but because the quotients of adjacent terms possess the astonishing quality of approaching the number 1.618 phi. We're not going to go on a quest for the Holy Grail. We're also not going to look at the role of the golden ratio in art history, although I'm told there is actually something there. So in 2002, before the Da Vinci Code came out, Mario Levi, a respectable popular science writer, wrote a whole book on the golden ratio, in which he says, "In fact, it's probably fair to say that the golden ratio has inspired thinkers of all disciplines like no other number in the history of mathematics. That does not include me. I have barely given it a moment's thought, and we're only really going to do the continued fraction stuff today." To set the scene, I'm going to hand over to Chris, who's going to show us how you derive the golden ratio, and we're going to establish that its number is 1.6, whatever it was. 1.618? Doesn't matter. Thanks, Chris. We're going to start by looking at the definition of the golden ratio. Let's start by defining the golden ratio in terms of its historical property. And that is, if we have a rectangle like this, and we cut off a square, this is a square, then the rectangle we're left with should have the same proportions as the rectangle we started, the big rectangle we started with. Okay, so let's do some calculating to figure out what all that means. We can make this side 1. That means that for this to be a square, this side has to be 1 too. We'll call this leftover bit B, length B, and we'll call the whole thing length A because we're going to work with Latin letters until we get to the answer, and then we'll start calling it phi if we want to, okay? I prefer to write A than phi. So, the ratio of the big rectangle, let's just say that's A over 1, which is the same thing as A. We'll do that in a minute. And that's the same proportions as 1 over B. 1 is alongside here, A is alongside here, so A, 1 over B. And we also know that B plus 1 is the same as A, so we can write B equals 1 plus B equals A. Now, this first expression, we can turn it upside down. We can multiply both sides by B and divide both sides by A, if that's the way you like to think about it. We can just write B equals 1 over A. And then if we feed that into here for B, then we have 1 plus 1 over A equals A. Okay, that's the kind of expression we looked at last time when we were working with the square root of 2. And we're going to do two things. First of all, we're going to take this expression and we're going to make it into a quadratic, solve it, calculate the number and see if we can get 1.618 out of that, which we can. So 1 plus 1 over A equals A. So multiply everything through by A. A plus 1 equals A squared. A squared minus A, taking this A to the other side. Subtract A from both sides if you like that, is 1. Now, we could use a quadratic formula if we knew a quadratic formula, but I don't remember the quadratic formula. Not really my thing. So what I'm going to do is I'm going to say A minus a half squared. I'm just going to work out what A minus a half squared is, and you'll see why very quickly. It's A minus a half times A minus a half, which is equal to A squared, multiplying that term. Then we've got two of these essentially. We've got minus a half times A and minus a half times A. So minus a half times A, minus a half times A, plus a quarter from multiplying the two halves. And the reason we did this in the first place is we've got A squared minus A plus a quarter. But the A squared minus A term is exactly what we have here. So we can now say, for example,
a squared minus a is the same thing as a minus a half squared minus a quarter. So we're going to put that into what I'm going to call equation 1. We have a minus a half squared minus a quarter is equal to 1. We put the quarter on the other side. A minus a half squared is equal to 1 plus a quarter, which is equal to 1 is equal to 4 quarters, so we can do this, which is equal to 5 quarters. We can take the square root of both sides now, so we get a minus a half is plus or minus the square root of 5 over 4. Now the square root of 4 we probably know is 2, so this is plus or minus 5 over the square root of 2. So a is a half plus or minus the square root of 5 over 2. Factor out the 2's just for neatness. Plus or minus the square root of 5. In fact, we're going to use the plus branch because it's the right answer, and because it's positive, the negative branch would be negative. So phi is equal to a half of 1 plus the square root of 5. And this is not a very interesting or attractive way to write a number. It's one you see when people write the golden ratio because that's what it comes out to, but it's not very charming in itself. In fact, it's so bad that we're going to get a calculator out and figure out what that is. All right, turn the thing on. Now I don't type everything into the calculator. I work in a fairly odd way. That's the way I used to work in the 1980s when calculators were still a thing and I was still a thing, and everything was very different. So what I do is I put in 5, and on this calculator I want to evaluate that first, and then I say, okay, fine, I've got 5, now I want the square root of 5. I take the square root of the previous thing, and then I say, okay, I want to add 1 to that, and now I take half of that by dividing by 2. And this is our number. Is it readable on the screen? I think it's more or less readable. It's 1.618, and of course the decimal expansion continues from there. Robert Langdon doesn't seem to know that there are more digits, or maybe he just doesn't care, or maybe he doesn't think his readers or audience would care, but there are plenty more digits where that came from. It's not a very it's not a number that stops. It's an irrational number, so it never stops. That's another story which we can talk about another time, although I'd really rather not. That's the art historical version of the golden ratio and its decimal expansion, and we'll go back to Chris to start talking about why Fibonacci has anything to do with any of this. Thanks, Chris. Last time we looked at calculating the golden ratio using a quadratic expression. This time we're going to go back to the equation we started from and do something else and derive a continued fraction representation. So let's start where we were. Where were we? 1 plus 1 over a equals a. Let's write that the other way around. Just change the order of things. Not very exciting. The thing is, what we're going to do this time is like what we did for the square root of 2 last time, only backwards. What we're going to do is we're going to say a is equal to 1 plus 1 over a, but we could substitute that in for this a as well. So let's write a equals 1 plus 1 over a there, and we're going to substitute that expression in for this expression a. So now a equals 1 plus 1 over 1 plus 1 over a. You see? You just put that value of a in where the a was. And we can do it again. We can put that value of a in here instead. And then we get 1 over 1 plus 1 over 1 plus 1 over 1 plus a. And I think you can probably see the pattern now. We could just keep doing this forever, right? I mean, in practice, writing it down forever would take forever, but we don't do that. All we're going to do is use the mathematical equivalent of writing it down forever. We're just going to go 1 over 1 plus 1 over 1 plus 1 over 1 plus, and then we just write dot 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 to mean keep doing that. And now this is equal to A, and this is our continued fraction representation of A. So we can look at that and see what that has to do with the Fibonacci sequence. But to do that involves more multiplying and dividing than I really want to do with a piece of paper, and even more than I want to do with a pocket calculator. So we're going to rev up the code engine and switch over to the code goblin, who's going to take over from here and show us how you calculate some of these things with Python.